This conference will now be recorded.
Yeah, it is taking some time to come. Okay, yeah, so it has come. So, Deepa, we had started the chapter atoms, and we had already learnt what is Rutherford's experiment and various models, like previous models, very preliminary models of atom was given by Thomson, and that was not satisfactory because it was not able to explain the line spectrum. Okay, line spectrum or hydrogen spectrum. Hydrogen or hydrogen like atom has their line spectrum or discrete spectrum, so those could not be explained using Thomson's model. Actually, Thomson's model was named as palm pudding model, or this that was, yeah, so that was called palm pudding model. Just like if you have a, like the model was, like model stated that the whole positive charges will be throughout the volume of a spherical object, and electronic charges will be distributed over or embedded in that. Just like if you cut a watermelon, then seeds are embedded in that. So the part what we eat, the red part, that is actually considered to be the positive charges. And like if I just try to draw it, let me, yeah, so suppose I have a half of that, so the part which generally we eat is actually considered to be positive charges, and the seeds will be there here and there distributed or embedded, those were considered to be negative charges or electrons. Okay, so this was the Thomson's model, but it could not explain the discrete spectrum of hydrogen or hydrogen like atoms. So that's why we had to discard it. We had to go for further investigations. So Rutherford, like on the suggestions of Rutherford, two of his colleagues, those Geiger, Marsden, Geiger and Marsden, both of them carried out alpha particle experiment and alpha particle scattering experiment, and Rutherford actually analyzed that data and come up with a new model of atom. So we'll today, what we'll do, we'll just take up the significant results of alpha particle scattering experiment, and then what Rutherford had given the like about, like what model Rutherford gave about atomic structure and its limitations, and we'll actually learn what is Bohr atomic model or the postulates of the Bohr's atomic model over this Rutherford's atomic model. Okay, so just for you, Deepa, I'm just repeating a little bit this alpha particle scattering experiment. Actually, there was an alpha source bismuth kept inside lead box, and there was a through path or a window through which the alpha particle will be coming out, and alpha particles were collimated to get a fine beam. And this is a gold foil. The alpha particles with very high kinetic energy were actually directed to hit the gold foil, and this is actually called screen. Zinc sulfide phosphor material was there in this. This is actually called rotating detector also, rotatable detector. There was a rotatable detector also. Here you can see this. So this is the source of alpha particle. This is the lead bricks to collimate the beam, and after getting fine beam, this is the thin, very thin. This alpha particle, this gold foil has thickness of this much to ensure that the gold foil is of monolayer, monolayer sheet, monolayer of atoms. Okay, monolayer means only one layer of atom is there. That means this alpha particle will collide a single atom at a time. That's what was the idea. And after this collision, how the alpha particles are, like where the alpha particles are going after colliding with this gold atoms. So those atoms after collision, like the alpha particles after collision were actually detected by, see, this is a detector with a microscope. So this is the phosphor screen. When the alpha particle passes through the gold foil and then hit this at various angle with respect to its initial direction. This is the initial direction of alpha, and when it is actually after collision with gold foil or gold atom, I can say, its direction will be deviated from its original direction, and at various angle we'll find out the number of alpha particle hitting the phosphor screen. Okay, phosphor screen. Okay, so upon hitting it will actually ignite some kind of light that is called scintillation. So those scintillations we can look through the microscope, and we can find out at which, like at what angle, how many alpha particles are coming out after passing through this thin gold foil. So what was the observable in this? Observable was number of alpha particle, number of alpha particles, passing, or I'd say not passing also. Some alpha particle will not pass that. So number of alpha particle and the angle of scattering, that is called angle of scattering. So these are two parameters which we were, like, Geiger and Marsden, in this alpha particle scattering experiment, they were noting these two parameters, and then they will plot the number with respect to, or with the angle of scattering. Angle of scattering means what? Suppose you were going in this way, but your path is getting deviated from your original direction. This angle is theta. This is called scattering angle. Okay, in this case, theta is shown here. You can see that. So this scattering angle, number of alpha particles with scattering angle, if you plot, if you see, so the plot will be kind of this. So at very low angle of scattering, the number of alpha particle will be very, very high. At higher angles, it will be decreasing like anything. And at 90 degree, or theta at 90 degree, or at 180 degree angle of scattering, number of alpha particle will be very, very less. So that is what is shown here. Look, the most of the alpha particle. So what are the significant results? The most of the alpha particle passes straight through the gold foil, or suffer almost no deflection. See, at very low angle means what? So see, gold atoms are there, suppose, in the foil like this. Okay, then alpha particle comes, and if they don't get scattered too much, then they go like this. Okay, almost no scattering. If they scatter and all, then path, see, so they can be deviated, their path can be deviated too much. So at very small angle, the number of alpha particles are very, very large. That means most of the alpha particle are actually suffering no deflection. Then very few alpha particles, like 1 in 8000 gets 90-degree deflection. Okay, get deflected by 90 degrees. That means 90-degree deflection means this way or this way. It is very, very less. Okay, 1 among 8000 can be seen. So it is here, somewhere here. Okay, so this is how the number of alpha particle with the angle of scattering decreases. And see, a head-on collision, that means alpha particle goes directly and hit and come back. It is, so this is called 180 degree. So alpha particle goes, hit the nucleus or the atom and come back. This happens for very, very less in number, or that is occasionally happening, it is said here. So 180-degree angle of scattering, at 180-degree angle of scattering, number of alpha particle is very, very small. So from these three main experimental observations led Rutherford to give some conclusion, or conclusion about the structure of the atom. See what he predicted. See, suppose this is a single alpha particle, sorry, a gold atom. Suppose this is a single gold atom, as you see in this, and there is a beam of alpha particle, means there are many numbers of alpha particles are coming and hitting the gold foil. That means there is a possibility to hit the atom. So when it is hitting the atom, see, most of the alpha particle were passing through. That means what? The most of the space within the atom must be empty. Most of the space within the atom must be empty. Then the so that's why we have seen that the most of the alpha particle passing through straight without much deflection, or without even without any deflection at all. And the positive charges and the masses of the atoms is concentrated. So what he concluded from there is that, see, from these three experimental observations led Rutherford to conclude these points. Most of the space inside the or within the atom must be empty. That's why most of the alpha particles are passing through. Positive charges and mass of the atom is concentrated in a very, very small region called nucleus. See, this second and third point, large angle scattering. So to see, in the large angle we see very, very less number of alpha particle to be scattered. Okay, from the graph we have seen. So this actually implies that the atom is empty, we have seen already, but some alpha particles are getting scattered by large angle. That means there must be, alpha particle is a positive charge, so it has two electronic positive charge. Okay, and nucleus is also a positive charge. If there is a positive charge, then only there will be a large angle scattering. That means if your nucleus is there, or at a very small region, so this is what Rutherford is saying, that at a very small region there is a positive charge of the atom, whole positive charge of the atom, which is actually deflecting the alpha particle at very large angle, either 90-degree or 180-degree. Okay, and when there is a 180-degree scattering, you can see, then you will see there will be head-on collision with the nucleus. Okay, head-on collision of the alpha particle with the nucleus. So that is what is this one. And mass, so he supposed that the whole positive charge and the almost the all mass, the whole mass of this atom may be concentrated at this tiny region or a very very small region that is called nucleus. A nucleus is surrounded by cloud of electrons whose total negative charge is equal to the positive charge of the nucleus. So this is the third conclusion what Rutherford made is that the nucleus, see, atom is actually, we have seen that positive charge may be there inside at a very tiny region. Maybe the whole positive charge is concentrated at that. That is very fine. But atoms are neutral in nature. Atoms are neutral in nature. And also Thomson had proved that there are electrons in the atom. So electrons must be there somewhere. So Rutherford had concluded that the nucleus is surrounded by clouds of electrons and the whole positive charge is actually getting neutralized by the total charge negative charge of that negative cloud, okay, such that the nucleus such that the atom as a whole will be neutral. So these were the conclusion. Now based on this conclusion, Rutherford, okay, so before I go to Rutherford's like model of atomic structure, I'll tell you one more important parameter that is called okay, so that is called impact parameter, and also we'll learn one more thing that is called distance of closest approach. So what is this? See, Rutherford had already proposed that there is a nucleus inside the atom, but he could even estimate the size of the nucleus also. Not only he had predicted, but he had given the size of the, like, estimation of the size of the nucleus also inside the atom. So how could he do that? He had actually calculated the distance of closest approach. Distance of closest approach means what? We'll discuss that. See, we know alpha particle has positive charge, and see, we have seen the nucleus also has almost the whole positive charge. Nucleus also has positive charge. Okay. Now, in case of 180-degree scattering, that means when the nucleus, sorry, alpha particle comes towards the atom, it sees the nucleus over here, positive charge, and it to come closer to nucleus, and then due to electrostatic repulsion, this alpha particle actually scattered back, or it will be retracing its path, giving rise to theta is equal to 180-degree. This is called head-on collision or 180-degree scattering. I'll repeat this. See, alpha particle, it is a positive particle, or it has a positive charge, and nucleus also has a positive charge. When alpha particle, in case of 180-degree scattering, what may be happening? The alpha particle having certain kinetic energy, suppose 5 MeV, so it is coming with this much kinetic energy with certain velocity, so with great velocity, and it is actually entering into the atom and come very close. Suppose it is r0 distance away, it comes up to r0 distance from the nucleus. So this distance is r0, this you can see. So this is the distance called closest approach, distance of closest approach. And what is the physics behind it? Because the alpha particle and the nucleus both are positive particle, so they will actually repel each other according to Coulomb's repulsive force, okay, or Coulomb's law. So they will be repelling each other. And see, when the alpha particle comes with great speed, because of the repulsion due to the nucleus, it will lose its kinetic energy. And what happens? It continuously loses its kinetic energy, and where that kinetic energy goes, actually kinetic energy gets converted to potential energy, electrostatic potential energy. Electrostatic potential energy. It gets converted to, so kinetic energy gets converted to electrostatic potential energy, and when this kinetic energy of the alpha particle, whole kinetic energy of the alpha particle gets converted to electrostatic potential, then it will actually stop for a moment at this particular distance r0 from the nucleus, which is called distance of closest approach. Further it cannot go towards the nucleus, and see, it will actually momentarily stop at this distance, and then it will revert back, or it will retrace the path. Okay, or it will come back. Like if you have a elastic ball, and if you just hit the wall with certain velocity, so with the same velocity it will come back to your hand if the wall is also having some elastic property. Okay, similarly here is happening that the alpha particle gets scattered by or repelled by the electrostatic force given by the nucleus, and the whole kinetic energy actually getting, see, kinetic energy will be, it will be, alpha particle will be losing its kinetic energy gradually, and it will come up to this much distance r0 from the nucleus, where its whole kinetic energy will be converted to potential energy, and then it will actually stop for a while at this particular distance, and then it will retrace back its path. Okay, so this is called distance of closest approach. And why does, what is the use of this, measuring this distance of closest approach? We can estimate the size of the nucleus. We can estimate the size of the nucleus from this distance of closest approach. So look, see, we have taken gold atoms. Okay, so gold atom, they have Z some 79 into E electronic charge, right? And see, alpha particle, they had, suppose this is 2E. Okay, I take this. Okay, so I'll just go with in general formula first, and then we can take a particular example to find out this. See, as I said, at this particular distance, the whole kinetic energy of the alpha particle will be, I am writing like this, alpha particle, kinetic energy of the alpha particle will be getting converted to potential energy. So electrostatic potential energy at this particular distance, if we find from the nucleus, then it will be, see, if suppose this is Z into E, this is of the gold, and I have 2 into E of the alpha particle, and then 4 pi epsilon naught q1 q2. We know the electrostatic energy will be actually given by q1 q2 divided by 4 pi epsilon naught r is the distance where we want to calculate the electrostatic potential energy. So here r is actually r0, 4 pi epsilon naught r0. Okay, so now using this equation we can find out, see, if we simplify a little bit, we can find out, see, we can find out r0 from here. So Z, we write 2Z square. Z is the actually the atomic number of the gold or anything, any foil we use. So here it will be 4 pi epsilon naught into K alpha. K alpha is the kinetic energy. So if we write K alpha to be 1, like half mv square, v of alpha particle, okay, square, then we can put it here. So half will go to the top, like in the numerator it will be 4, and here I can write, instead of K alpha, we we can write m alpha v alpha square. So you can see that closest approach, actually, see, distance of closest approach is inversely proportional to the mass of the alpha particle, and also it is inversely proportional to the velocity or the speed with which it comes. Okay, velocity square, in fact. Okay, velocity square. So these are the parameters. Yeah, so if we just put the value, suppose for a particular alpha particle scattering experiment, if we know the kinetic energy, suppose okay, let me write the original k alpha over here, and look, this was 2 over here, and z will put for gold. So if we put z is 79, then 2 into e square means 1.6 into 10 to the power minus 19 whole square divided by 4 pi epsilon naught. This will go as 9 into 10 to the power 9. Now, if the kinetic energy is 5.5 mega electron volt, that means 10 to the power 6 into 1.6 into 10 to the power minus 19. Okay, so if you solve this, so you will get this distance of closest approach nearly. If you take this k alpha to be 5.5 MeV, okay, a typical alpha particle experiment in which the alpha particles are having 5.5 million electron volt energy, kinetic energy. So if you just calculate this, you will get something like this. This is the femtometer. Femtometer, Fm means 10 to the power minus 15. So this is the kind of closest approach could be obtained for this much, like for this much energy of alpha particle. Okay, so look, this femtometer, this gives an idea that how tiny the nucleus is. So distance of closest approach, sometime you will be asked to find out the size or distance of closest approach. So you have to actually use the general formula. I'll write once again. So 2z square divided by here 4 pi epsilon naught and the kinetic energy of the alpha particle. So this is the formula you have to use if sometime you are asked to calculate the distance of closest approach and estimate the size of the nucleus. So this is actually from this particular experiment, like example, we have got this to be 10 to the power minus 15 meter. So this 10 to the power minus 15 meter is written as femtometer, femtometer Fm. Okay, femtometer. So that's why I have written 41.3 femtometer. Okay, so this is the significance of calculating distance of closest approach. So from here, at least we can say what we can say. We can say that the nucleus has the size less than, so yeah, less than. So so radius of radius of the nucleus will be less than this much femtometer. Okay, this much femtometer. Now we'll learn one more thing related to this alpha particle scattering, that is called impact parameter. So this impact parameter is very important for scattering, or yeah, scattering, alpha particle scattering. See what is the definition of impact parameter? Impact parameter is defined as the perpendicular distance of the initial direction of the velocity or velocity vector of the alpha particle from the center of the nucleus. I'll show you the figure, then you will be appreciating this definition. So impact parameter is defined as the perpendicular distance of the initial direction. See this, the initial direction or initial velocity vector of alpha particle is this one, right? This is the initial before it gets scattered by the nucleus. Here this is the nucleus. Okay, this is the nucleus. Suppose this is representative figure. Okay, so this is the alpha particle which has a velocity vector in this direction, or the direction of the velocity initial direction of the velocity is this and this is the final direction, final direction of the velocity. Okay, this one. So we have to have this direction, okay, and then we have to draw a perpendicular till the center, okay, uh, to the center from this direction. So the perpendicular distance, see, look, this perpendicular, this is called perpendicular distance alpha perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. That particular distance is called impact parameter. So impact parameter is defined as the perpendicular distance of the initial velocity vector from the center of the nucleus. So this is called impact parameter, and as you can see, the impact parameter is denoted by B. So impact parameter, we'll write here. Impact parameter is denoted by B. Okay, in general, impact parameter is denoted by B. Okay, so mathematically, Rutherford had proved that this impact parameter B can be written as 1 by 4 pi epsilon naught Z square cot theta by 2, that is the angle of theta is the angle of scattering, theta by 2 divided by k is the kinetic energy of the alpha particle, k is the kinetic energy of the alpha particle. So sometime maybe these parameters will be given, kinetic energy will be given, so and also theta may be given. You have to find out what is the impact parameter. So impact parameter B is mathematically defined by Rutherford in this way. So z square into cot theta by 2 in the denominator 4 pi epsilon naught into k. K is the kinetic energy of the alpha particle, that is half m alpha v alpha square. Okay, so this is the mathematical expression for impact parameter. Now look, we will have, see, there are few things to note here. See, if the impact parameter is very, very large, that means if the alpha particle goes at very large distance, suppose this is the path, initial direction, then I'll just remove this portion. Let me remove this. So impact parameter large. When the impact parameter large, that means this B will be large. That means the alpha particle which are actually passing through this direction, this is actually having a large distance from the center of the nucleus. Okay, so if the impact parameter is large, then see how scattering is happening. We know alpha particle is positive particle, and this is also positive, so repulsion by electrostatic repulsion. So if the alpha particle is very, very far, okay, very far away from the center of the nucleus, okay, then what happens, the repulsive force will not be affecting the direction of the alpha particle, so it will almost go without any deflection, but as you can see from here, when the impact parameter is really small, then this repulsive force will be affecting the motion of the alpha particle, so it will be strongly scattered. The direction of the alpha particle will be actually changed to a great extent, or large angle of deflection will be obtained. See, this is the theta angle of deflection. So if the impact parameter is small, deflection is more, or the scattering is more. Okay, and see the last point, see, when there is a head-on collision, that means the alpha particle coming in this way, then what will happen, it will be rippled back or retracing the path. So then you will have theta, or angle of deflection or angle of scattering, to be 180 degree. So in case of head-on collision, this is called head-on collision. So in case of head-on collision, impact parameter will be 0 for head-on collision, or 180 degree reflection. Head-on collision or 180 degree deflection. Okay. So impact parameter will be 0 for 180 degree deflection or head-on collision. So I'll just write this B finally once again. So look, this is Z square cot cot theta by 2. Here it will be 4 pi epsilon naught into K alpha, kinetic energy of the alpha. So this is the mathematical expression, and these are the points we have learned. So in case of, see, in case of head-on collision, the B will be 0. Okay, so these are the few points we had to learn in this. Now what we'll do, we'll see the atomic structure what Rutherford had given the conclusions based on the conclusions of the alpha particle scattering experiment. So we had seen these conclusions that the most of the space within the atom will be empty, then positive charge and the whole mass will be concentrated at a very small region which is called nucleus, and electrons are actually surrounding the nucleus as a cloud. Okay, those conclusions we had seen. So based on those conclusions, Rutherford had given the model of atomic structure. Let us see. So the first postulates or the first statement of his model is that atomic model is that an atom consists of a small and massive center core in which the entire positive charge and almost the whole mass of the atom are concentrated. So the whole positive charge and almost the whole or entire mass of the atom is concentrated at a very small and massive central core of the atom. So that is called nucleus. That core is called nucleus, right? And we have seen what is the size of nucleus. So size of nucleus we had seen some femtometer. Okay, femtometer means it is having dimension of the order of 10 to the power minus 15 meter. Okay, and what is the dimension of atom? Say atomic dimension, actually dimension is atom's dimension is of the order of angstrom, actually some few angstroms. So it is of the order of 10 to the power 10 meter. 10 to the power 10 meter. This is femtometer, this is meter. So you can see, so almost 10,000 smaller, 10,000 smaller, like by, so the nucleus is actually smaller by a 10,000 factor, right? So size of the atom is very big, bigger than the nucleus. So almost 10,000, or yeah, so almost 10,000, of the order of 10,000 factor. Okay, that means, see, atom size, if I say the atom's diameter is d, okay, then 1/10,000 or 1 or maybe 10 to the power 5. So this will be the size of nucleus. Okay, nucleus radius of the nucleus. Okay, all right. So this was the first postulate, that it consists of small massive core which is called nucleus. Okay, and where the entire charge, positive charge, and the whole mass is concentrated. The second thing is the nucleus is surrounded by a suitable number of electrons. See, there will be electrons surrounding the nucleus, but there should be a suitable number such that the total negative charge is equal to the total positive charge of the nucleus, and that's how the atom as a whole will be electrically neutral. Okay, so that was the situation. So nucleus is surrounded by suitable number of electrons, and their total negative charge must be equal to the total positive charge on the nucleus. The atom as a whole will be neutral. Now the last postulate is that the electron revolve around. So see, we have seen, we have already learned learned from Thomson that there are electrons. An atom is neutral, so there must be positive charges also. But if there is a positive charge, what will be the distribution? How the structure of the atom would be? So to answer that question, actually Rutherford had conducted the alpha particle scattering experiment. From the conclusion of that, he had proposed these 3 points. So we have learned 2 points. One is that existence of the nucleus. Then we have seen how the electrons are distributed according to Rutherford, that electrons are surrounding the nucleus, and how they are distributed there, like that is stated in the last point. The electrons revolve. Okay, electrons revolve around the nucleus in various orbits, just as planets around the sun. So how electrons are distributed, that is the main point. The main point is that the electrons will be surrounding the nucleus, but how they will be distributed? They will be actually revolving around the nucleus, just like planets do in case of planetary system. What 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 is done in case of what is happening in case of planetary system? You see the figure. So this is, so that's why the Rutherford's model is called, Rutherford's atomic model is called planetary model of atom, planetary model of atom or atomic structure. Okay, generally it is called planetary model of atom. So that was given by Rutherford. So what is, so the main point is this one, that the electrons revolve around the nucleus at various orbits, just as planets around the sun. Then there will be a question. So these orbiting electrons must be provided centripetal force such that they will actually revolve around the nucleus. So from where is that obtained? So the electrostatic attraction between electron and nucleus is actually providing the required centripetal force for this revolution of the electron around the nucleus. Okay, so these are the main points in the Rutherford's atomic model. Now see, there are actually, there is a very serious flaw in this, very serious flaw. We'll see there are mainly two limitations. Now we'll see there are two limitations mainly. First is that we have we have got uh, we have got the point here is that the nucleus is at the center and electrons are orbiting at various orbit. That is what we have learnt now from the Rutherford's model. But see, electrons are not like the planets. See, planets, it was actually imitated the, like in the Rutherford model, actually imitating the planetary model of solar system or planetary model. Okay, but see, the planets are actually neutral. Planets are neutral. That means no charge. They don't have charge. Okay, planets don't have charges. Okay, that's why when they are revolving around a circular orbit, nearly circular orbit, let us take uh, for here the orbits are circular orbits. In fact, he spoke about circular orbit only. So if you recollect the circular motion, we know we know a particle which is undergoing a circular motion, it has a centripetal acceleration. That means the particle is actually moving with uniform velocity, uniform sorry speed, uniform speed maybe, but it has an acceleration that is called centripetal acceleration. So the planets are neutral even if they have some centripetal acceleration doesn't happen, like doesn't matter for them. But when you have electrons which has acceleration, that means I can say electrons are accelerated. So we have learned in electromagnetic, like electromagnetic wave chapter, the origin of electromagnetic wave or the source of electromagnetic wave is actually source of EM wave is accelerated charge particle or oscillating charge particle. Accelerated charge particle, charged particle, or oscillating charge particle. So electrons are here charged particles. Since they are revolving around the nucleus, they have centripetal acceleration, so they are accelerated. So what would happen here? Accelerated charge particle, according to classical electromagnetic theory, they will radiate energy, electromagnetic, in the form of electromagnetic wave. Okay, as you can see from here, these are EM wave. They will be radiating the energy. Suppose this particular orbit has certain energy, this also has certain energy but different from this. Okay, so this energy will be continuously radiated. This is the inner orbit, this is the outer orbit. See, inner orbit has lesser energy than the outer orbit. Okay, so when every orbit, like every electrons, whatever may be the orbit they are revolving in or revolving around, they will be radiating energy. And continuously radiating energy, what they will do, they will be losing the energy. And as they lose the energy, see, they start from highest orbit, then they will be actually losing the energy, and eventually they will actually fall into, like fall onto the nucleus. Finally the electron should follow a spiral path, and finally it should collapse into the nucleus. So then there will be no stable or stationary atomic structure. So the existence of the atom will be itself constant. So the first limitation was this one, that Rutherford's model could not explain could not explain the stability of an atom. Explain the stability of an atom. Okay, and the second thing is that since electrons will be spiraling inward, their angular velocity and frequencies would change continuously. So, so you can see that they will be actually radiating continuous energy. They will be losing energy in continuous manner. So angular velocity or the frequency will be changing continuously. Okay. So frequency emitted, or the see the radiation emitted, radiation emitted by an atom would give a continuous spectrum, give a continuous spectrum, continuous spectrum. Okay, so these are the two flaws, but we have seen, but in actuality hydrogen atom exhibits discrete 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 spectrum. Okay, discrete energy spectrum. Okay, discrete spectrum, hydrogen atom or any other atoms. So atomic spectra has been seen that atomic spectra are line spectrum or discrete spectrum. So these are the serious flaw which could not be explained from Rutherford's model. To remove these flaws, Bohr will come up with atomic model but with quantum idea. So he will be taking up Rutherford's idea as well as he will take up the idea of Planck, Max Planck, Max Planck's quantum idea. So both this Rutherford's atomic structure and quantum idea in combination, Bohr will give a new model of atomic structure which is called Bohr's atomic model. And Bohr had given mainly 3 or 4 postulates to just to actually just to give the explanation how the atom will be stable, the structure of the atom will be stable, and how discrete energy spectrum can be explained. So these two things, aspects, he had actually took up, and then he could, like, he explained with the quantum idea how the energy spectrum can be discrete and how the stability of the orbits can be, or atomic structure can be explained. So we'll see Bohr's atomic model in the next class. Like, all the postulates we'll be learning, okay, and we'll see how discrete spectrum can be obtained from the Bohr's atomic model, or explained from Bohr's atomic model. So we'll stop it here for today. Deepa, if you have any question, you can ask me now. So today we have recapitulated the Rutherford's alpha particle experiment and its significance, like significant results, and from there how Rutherford predicted about the atomic structure. That means the atomic model we have seen, and we have seen what are the limitations in that model. In the next class, we will try to remove, like, we will try to understand how to, like, how Bohr had addresses addressed these limitations with the quantum idea. Okay, all right, Deepa, so do you have any question? So if you don't have any question, I'll stop it here for today. You can ask me any other day also if you have any doubt. Please read this whatever we have discussed today. In the next class, we will be learning Bohr's atomic model. We thought of doing it today, but it took little extra time. So, all right. So, bye for today. Okay, I have got your response. Everything is clear. All right. So, bye for today.
Thank you, sir.